In this video, I'm going to show you how to set up a parameter fitting spreadsheet so that you can determine what the parameters in an experimentally found data set are. So to explain this, an experiment was done and values of an independent variable x were used in the experiment. Response variables or outputs of the experiment were recorded for a variable y. So when one was to plot the data using Excel's scatter tool, so this is insert xy scatter, we can plot this data and see how the data set looks. Now in the other video I showed where charts should be located on a sheet that is properly labeled. As an individual sheet, that axes should be properly sized. So in this case I want to change the minimum of this axis to 6.0. I can leave the maximum where it's at, and I then want to do a similar exercise and change the minimum of this axis to, let's say, 90. So now the data occupies a larger portion of the chart area. We should use Excel's styles to be able to add titles and to edit titles, such as experimentally found y versus x, and we can always add titles to the x-axis and the y-axis. So in this particular sheet we have our data set, and we can see that y is just numeric values found by experiments. So what is the goal of data fitting? The goal of data fitting is to find a mathematical expression that represents this data as well as possible. Excel has built-in tools to do this. So the way you do this in Excel using the built-in tools is you select the data, you right click, and you say add trend line. Now Excel adds a linear trend line by default. So we want to see what the equation is for this line. So we say display equation on the chart, and we also want to click display r squared value. Now when you do this, an equation pops up on the screen, and that equation has in it a form. This form is y equals to mx plus c, the equation of a straight line. The r squared value here represents the goodness of fit. What that means is r squared is actually calculating an average distance of each point from the line, and it is telling you how that average distance or residual or the square of that residual measures up in comparison to the average of the entire data set. Clearly one can see these values are somewhere between 6 and 16. In this case, residuals would be of the order of 1, 1.5, 0.5, very small residuals. If the output was rather 60,000 to 160,000, then these residuals can have very large values. So in order to make sense of the data, the residuals are compared to an average value for the data set. There are many different trend lines available. So by selecting the trend line, and then selecting this tool here, which is trendline options, we are able to choose what form the trend line should take. In this case, the equation has changed to the form of some constant multiplied by the exponent raised to some power multiplied by x. We can see that the r squared is 0.2967. An ideal r squared value would be a value of 1, meaning that the residuals are 0. Here we can see, in this case, it is linear is a slightly better fit. Logarithmic is an even better fit at 0.3834. A polynomial second order, being a term in x squared, x, and a constant, gives the best result so far with an r squared of 0.5538. And the power option is again terrible. Now, the polynomial second order is a fairly bad fit still at 0.55. If we raise the power and make it a cubic equation, we are able to get a better fit, but still not a great fit. One could continue to raise the order and hope to get an even better fit. In this case, there is no significant change in the r squared value between a third order system and a fourth order system. So any user of the information provided by these experiments would be able to put in a value of their independent variable into this function and would be able to determine what the output of the experiment should yield. In some cases, the experiment is actually done with the knowledge that the data should be represented in a specific mathematical form. In this case, that form is y equals to ax over x minus b to the power of c. The key here is to determine the values of a, b, and c such that the residual error is very, very small and the r squared tends to 1, which is a very good fit. So in order to do this, we start by establishing 3 values, an a, a b, and a c. And we will take initial guesses at what these values are. In this case, 1, 1, and 1. Now, these are clearly wrong. And we know that because if we substitute these values into this equation, y will be incorrect. But let's do it anyway. So we put in a y predicted, and I'm going to make that a subscript. So we have a y predicted, and that y predicted is going to be equal to a multiplied by the value of the independent variable, and I'm going to divide that by the independent variable x minus b, all raised to the power of c. Now, Since I intend to drag this formula down, I would like to keep absolute references for A, B, and C. So in order to do that, I select E2 and make it $E $2. Now there's a fairly simple way to do this in Excel. I can also select the cell address and press the function 4 key on my keyboard, and Excel will insert the dollar signs appropriately. Now I can hit enter, and the value calculated by the formula can be dragged down, and we can see the formula will be correctly set up in each case. So we've calculated a y predicted. So what we should do next is calculate a residual error. And a squared residual is what we should calculate. So I'm going to call that square res. And in this case, I am going to say this is equal to the difference between the predicted and the actual, all squared. Now, why do we square it? We square it because we want every error when we sum them to contribute towards the total error. If some of the errors were negative and some of the errors positive, what would happen is some errors would cancel other errors out, and we want to avoid that. So at the very bottom here, we wish to have a sum of square residuals. And that sum of square residuals, we're going to use Excel's sum function. We're going to search all Excel's functions for sum, and sum is going to tell us the total of this column. And there we have a sum of residuals. Now our goal is to minimize this sum of residuals. Another important value that we want to get is that r squared value. Now the formula for the r squared value is 1 minus the square of the predicted minus the average of these values divided by the sum of square. So here's what it looks like. I'm just going to insert a formula for r squared to show you. So insert equation, and in this case we're going to say that r squared is equal to 1 minus the sum of square residuals divided by the sum of square total. And we'll see where we get these values from in a second. So we want to find an r squared that is 1. So in order to find the sum of square totals, what we need is an average of the actual experimental values. So I will select another function. In this case, I want to use the average function, and I want to find the average of all the response variables or the outputs of the experiment. And we can see that the experiment has an average value of 10.28. Now 10.28 squared is 100, and essentially 100 is very different from this very big value. So we're looking for a sum of square residuals that is much less than 100. So we're going to find this SST. So SST is actually going to be equal to the found y minus the experimentally found average. And in this case, we want an absolute reference to this average because we want every y found relative to the average. And we're going to square that. Next, we're going to continue this formula for the entire data set. Now we're going to find this value, which is going to be SST, as the sum of all of these values, and I can simply scroll across this way and you can see it finds the sum of E4 to E34. Now clearly these values are very, very big. Next, we're going to find what the R squared value actually is, and that R squared value is going to be given by the formula 1 minus the sum of square residuals divided by the total. In this case, we have a terrible R squared value, but we haven't found the ideal values for A, B, and C. So before we move on, what I'm going to do is I'm going to neaten up my spreadsheet just a bit, and now we can go ahead and find values for A, B, and C. One can try to find these values manually, or we can use the function that is available in Excel, which is a solver. To find the solver and make sure it's installed, you go File, Options, you go to Add-ins, and you click Excel Add-ins Go, and you enable the solver add-on. Upon doing this, Excel will add a solver item to the data menu. This item would not have been there before. On clicking the solver item, a window comes up, the solver parameters window. Your objective is to set this cell, which is your sum of square residuals. Your objective is to set that cell to a minimum value, and we want to be able to change the values for A, B, and C until we reach that minimum. We can add constraints, but we will leave those out for now, and we will solve. Solver has converged to a solution, meaning that solver will have found a value of A, B, and C that reduces the sum of square residuals to a minimum value of 17. You can say keep it, and in this case we have an R squared calculated of 0.66, not a great fit, but a fairly decent fit. If we want to see what that looks like, we can then plot all three data sets. In this case, the X versus Y predicted. And we will plot that using a scatter chart. I'm just going to move this chart and put it on its own sheet, which is fitted data. In this case, we want a straight line to represent this data set, and we don't want any markers. So this straight line represents the equation that was fitted against the data set. Clearly, errors still exist between the actual experimental values and the predicted values. The straight line represents the predicted values, and the dots represent the experimental data points. So we have found that this equation, although not perfect, does to some extent represent the experimental form here. And the values of A, B, and C are such that they were found by the solver. And that is how we do data fitting or multi-parameter fitting in Excel.